is Math 139, Preliminary Section 5. We're looking in this section at systems of linear equations, which means we'll have more than one equation that we're trying to solve. Our systems will consist of two linear equations, and we already know how to graph a linear equation. And so let's imagine that we've got our two equations and we've actually graphed them right here. Here's the first one, here's the second one. There's one point right here where these two lines intersect, and that's what we call the solution to the system. Why do you think we call it that? What's special about that point? Well, that particular point is the only point that actually is a part of both lines. So it solves the two equations simultaneously. It makes both equations true. All right, we're going to look at several methods for solving a system of linear equations. And the first one is called the substitution method. In order to do this method, what we're going to do is take one of our two equations and solve for example, y, and then use that result to substitute for y in the other equation. In fact, we can actually solve for any variable. We could solve for x, or if our system happened to have other variables instead, we could solve for any variable we wanted. But at least in this first one, I am going to solve for y. Taking a look at this example, what I want to point out to you is that it's really easy to get the y by itself. It's easy to solve for the y in that equation. Typically, that's what I look for when I'm trying to solve a system by substitution. I look for a variable that's easy to get by itself. So let's do that first. In this case, if I simply subtracted the 3x, my equation would look like y equals negative 3x plus 10. And then what I'm going to do is I'm going to look for where the y is in the second equation, and I'm going to literally replace that y with what y equals, negative 3x plus 10. So the second equation becomes 5x, and then I've got a multiplier of minus 3 times, and now instead of the y, I'm going to plug in the negative 3x plus 10. And then that equals negative 2. I still have an equation to solve, but I now only have one variable. So let's go ahead and do that. We've got 5x, and then distributing the negative 3, I'll get a plus 9x minus 30 equals negative 2. So I've got 14x minus 30 equals negative 2. And then just finishing that one up, I'll add the 30 to get 14x equals 28. And dividing by 14 is going to give me x equals 2. I've done most of the work, but I've actually only got half the solution. There were two unknowns here, both x and y, and right now I only have the x value. To get the y value, I usually just go ahead and substitute that back in to the original equation once I had it solved for y. And so I'm going to get y equals negative 3 times, and I'll plug that 2 in for x, plus 10. Negative 6 plus 10 would give me a y value of 4. So the solution to this system is x equals 2, y equals 4. That one point will make both equations true at the same time. Because we often still think of this as two lines with an intersection point, we very often write the solution to a system of equations as a point, x comma y. And so I'm going to write the solution as 2 comma 4. Systems of equations can arise in application problems, including modeling problems. And so we'll look at an example of that next. In this problem, we're looking at a principle in economics called the law of supply and demand. It basically states that as the price of an item increases, the demand will decrease, but supply will increase. Makes sense, right? If the price goes up, probably fewer people are going to buy, so the demand decreases. But on the other hand, if you can make more money on something, you're probably going to be more willing to manufacture it or supply it, so supply goes up. This data table shows daily sales, which would be the demand, of a particular brand of jeans for various price levels, as well as the available supply for the same prices. We're going to start by verifying that a linear model is a good fit for demand, and then find that line of best fit. So we're going to write it in the form N equals D of P. N is going to be our demand, so I'll put that right here. And P is the price. Okay, rounding everything off to 1 decimal place. All right, so we want to start by putting our data in and first of all just verifying that linear is reasonable. We'll do that with a scatter plot. So in Stat, I want to edit. I'll clear out my old data and put in the new. Price data in the first column. And then demand data, the number of pairs of jeans sold each day in the second column. First of all, I just need to verify that I do want to use a linear equation. So I'm going to go back to y equals, and I'm going to say, let's see, we've got our plot turned on. That's good. In the window, looking at the prices, they go from $20 to $30. I usually like to start with a 0 if I can, but in this case, the data is all kind of in that 20 to 30 range. So maybe I'll go from 18 to 32, just allowing myself a little bit of room on both sides. Scale of 1 should be fine. On the demand, looks like 60 down to 44. So let's see, maybe I'll go from 40 to 65. Scale of 1 should be okay. And graph. All right, it's not wonderful, but it's somewhat reasonable as a linear equation. I can kind of see a line in here that would come somewhat close. I'm not expecting a great correlation coefficient, but I don't think it'll be too bad. Let's go ahead and back in Stat again. I'm going to calculate my linear regression. L1 and L2 is where my data is. And you can see I do get a slope, negative 1.4 approximately, and a y-intercept of about 88.2. The r-squared value is 0.944, and that is reasonably close to 1. Anything over about 0.9, I'm really quite comfortable with. By the way, the negative r value here is because of the negative slope, but it's close to negative 1. So I'm going to go ahead and write my equation here in this form. N is equal to the demand based on price of negative 1.4p plus 88.2. All right, we want to go, actually, before we do that, let's do one other thing. We weren't quite as comfortable with the linearity of this data. Let me just go ahead and put that equation into my y equals, and just take a look at the equation that they actually found for me. It was negative 1.4, and I'll have to go with x, plus 88.2. And when you go look at the line that they found, you can see that although the points are a little bit off as we get toward the end, because the line kind of runs between them, it's actually not too bad a fit. All right, we're going to do basically the same thing for supply. This time our n value is supply, and I would like to get, once again, a linear model, a line of best fit. So going back into my stat, I'm going to edit my data, and I have a couple of options. First of all, the prices remain the same, so I don't need to change my first column here at all. I can change my second column to reflect this new supply data instead of the demand data that I had in before, or I can put the supply data in my third column. It kind of depends on whether or not I think I'm going to need this data again. Just for a little practice, let's use the third column. This is how many pairs of jeans manufacturers are willing to make at each given price point. All right, if I go in and do my calculation here, my linear regression, remember this time, even though my prices stayed in L1, the supply data was in L3. So I'm going to have to come back down here, and I'm going to have to go ahead and do L3, which is the second function above the 3 key. So second 3 gives me the third list. And there we go. The number of pairs of jeans for manufacturers at each price, S of P, is modeled rounding to 1 decimal point place as 1.7 P plus 14.9. Notice that this is quite a good fit. We've got R and R square values both running in that 0.99 plus range. So this one's a really good fit. All right. Well, you can imagine what happens if supply and demand are different. If we have more demand than supply, we run into shortages. If we have more supply than demand, stores end up with these items sitting on their shelves and nobody will buy them. So the ideal situation would be to have supply and demand be the same. And that's our question in Part C. At what price point will supply and demand be equal? We're going to solve this by hand using algebra, and then we might also look at a calculator solution. In these two equations, notice that right now they're both solved for n. I could simply take this value of n and plug it in for there, effectively setting supply and demand equal to one another. And so that's exactly what we're going to do. It's a substitution method. All right, let's go ahead and solve this. I'm going to start by adding the 1.4p to both sides. And let's subtract the 14.9. Let's see, that's 73.3. And then dividing by the 3.1, I'm getting 26 or 23.6. And actually, that's price. That's P, so I probably should keep another decimal. We'll round that off to 23.65. So at the price of $23.65, our model predicts that the supply and demand would be the same. Now, considering our original system of equations contained two variables, P and N, we've actually answered the question, but let's go ahead and calculate the value of the other variable, the N. I really have two expressions for N. I can use either one of these to plug in and get N. I'll just use this top one, negative 1.4, and I'll multiply that by the P value, 23.65, plus 88.2. And I'm getting 55.09. Although the problem didn't actually ask for it, I want us to think about what that N value is telling us. We've already said the price is $23.65. N represents either the demand or the supply, depending on which equation we had, but it's going to be the same at that particular price. So we're saying, if we round off to the nearest whole pair of jeans, that at a price of $23.65, manufacturers are willing to make about 55 pairs a day, and people are willing to buy about 55 pairs a day. In other words, both supply and demand. Are about 55 at this price. One other thing, I just wanted to quickly remind you how you can also use a calculator to solve this particular problem. When we have two equations, both solved for the dependent variable, like we do in this case, both of these are solved for n, we can actually graph both lines on our calculator, and we can find that intersection point, that point that belongs on both lines, using the calculator. So let's go ahead and do that. I'm going to turn the plot off because I don't want to see the points now. And I've already got the first line plugged in, negative 1.4x plus 88.2. So let's plug in this second line. 1.7. And again, my calculator doesn't have P. I have to use X. Plus 14.9. And there we go. We can clearly see the intersection point, but I can't exactly predict where it is. I didn't actually have the axes shown on here because of the window settings that I used. But even if I did, I couldn't estimate that accurately just by looking at the graph. So we'll use the calculator itself to find that intersection point. Above your trace key, we have this calc feature, and that finds a lot of stuff on graphs. So let's go second calc. And you'll notice that one of the options is intersect, which is what we want to do here. So I'll select that. It's going to ask you some questions. First of all, is this the first graph you want to use? It says first curve, but that's just what they say for graph. Since it is, I say enter. Is this the second one? Well, yes. I'm going to put enter again. And then it asks you for a guess. In fact, it's fine just to hit enter again, although if you want to, you can use the arrows to move your cursor a little bit closer to the actual intersection point and hit enter. And there we go. There's our X or P value, $23.65. And there's the N, the number of jeans, both supply and demand, are about 55 at that particular point. So there's a way to use technology to come up with the same solution that we were able to find by hand as well. We will pause here and continue this section in the next video.